Hello everyone, welcome back to the series of tutorials on geostatistics. Today we will be covering one of the most fundamental concepts in geostatistics, the concept of spatial declustering. We will also take this opportunity to learn some of the basic data types and spatial operations that GeoStats.jl provides. So here's the problem that we'll be addressing today. We will pretend that we are a mining company interested in extracting a mineral resource such as gold from a mine that I'm calling here D. Based on the fact that you're trying to maximize profit, we end up collecting samples S at nearby locations x1 through xn, where we believe we will find the mineral that we are after. Our data acquisition process suffers from sampling bias. Most of our samples reflect high concentrations of gold. Here's the problem statement. Estimate the remaining amount of gold in the mine D from the spatial samples S. And a related question could be, can we do any better to estimate this remaining amount of gold than multiplying the sample average by the volume of the mine? So I can take the sample average and multiply by the volume to get an estimate. Can we do any better than this? Here's the problem specified in the form of code. In the left, you see an image that I'm pretending is a top view of a mine, where the yellowish color represents high concentrations of gold and the bluish color represents low concentrations of gold. In the right side of this plot, you see a spatial sample taken from this mine. That's how I construct this problem. I load the GeoStats package, which contains all the spatial data types and operations we'll be using, and the GeoStats images package, which contains example images from the literature, like this one. We load the plots package for plotting and set the back end of the plots package to the GR backend and set a default color map to be the CVD's color map. We load an image from GeoStats image called the Walker Lake Truth image, and we save the first layer of this image in a Julia array. We then georeference this array in a GeoStats object, a regular grid data object, where we pass a dictionary mapping the spatial variables to the data, and we specify here the coordinates of this data set. So here is the coordinate of the lower left pixel, 0, 0, and here is the size or spacing of each of these pixels, 1 by 1 units. After we have this spatial data type, we can sample from this spatial data 50 samples. And in order to mimic the sampling bias issue, I'll be sampling with weights that are proportional to the amount of gold in the pixel. And I'll sample without replacement. I then plot the mine side by side with the spatial sample, as we see here. What we will notice is that if you take the mean of the gold in the full mine, in the full image, we will get a sharp 0.5. This is a synthetic image. Whereas if you take the sample average from the spatial data set, we will get a much higher value because of this sampling bias issue. So besides having this sampling bias issue, this data set also has an interesting property. You will notice that our sampling process leads to samples that are clustered in space. If you look at this image here, where you see that most of the yellow dots appear clustered compared to the blue dots that are more isolated, this is a side effect of the sampling process. Whenever someone samples in a location where the amount of gold is low, it's very reasonable to stop searching in the vicinity of this point and move to another area or another region of this mine. Whereas if you sample a point with high concentration of gold, you tend to keep exploring that region. In order to quantify this observation, we can, for example, partition these spatial samples into blocks of fixed size, b square, and then count the number of samples that share a block. So this is how it looks like in code. We can create a spatial sample a spatial partition B, which is the partition of the spatial sample S with a block partitioner. So I can select a block partitioner, and I'll set the block size here to be 50 by 50. So this operation creates a set of blocks. There are 29 non-empty such blocks, and each block has a number of samples inside them. So the first block has only one sample from a spatial sample S, but other blocks here have 5 samples, for example. As any other data type in GeoStats, or most of them, you can plot them directly. So you can plot these blocks to observe that each of them here is marked with a different marker type. So here we have a block with 4 samples with this diamond shaped marker, and here we have a block with just a single sample with a star marker. There's a warning here that I can omit by omitting the color bar, and then I'll also set the X label of this plot to be X and the Y label to be Y, the coordinates of this spatial data set. I'll save this plot in my plot 1, and then I'll go to the second step of this instruction here, which is count the number of samples that share a block. So we can access each block in this spatial partition, for example, by indexing. Here I'm indexing the first block, so if I do this, I get a data view of the spatial sample, which contains only one sample in it. And I can do this for any of the blocks 1 through 29 we saw. For each of them, I can take the number of points in this block. Oh, I forgot the S. And I can do this for every one of those blocks. Instead of doing it for each block separately, I can apply this function to every element of this collection by putting a dot here and omitting the index. So here I have the 29th length vector with the number of points in each block. I can then create a bar plot with these points, and I will omit the legend, and I'll set the X label to be blocks and the Y label to be counts. Okay, I can save this in my second plot, and then I'll plot both of these plots side by side, plot 1 and plot 2. I'll specify the size of this figure to be 900 by 400. So you will see that there are blocks 1 through 29. Most of them have only one sample, but some of these blocks have 5 samples, and some have 4, 3, and 2 samples. So samples that are close to each other, like these ones here, they are redundant. They have similar values of concentration of gold. They shouldn't receive the same importance in this mean estimate compared with isolated samples like these ones. We can use the block counts to assign importance weights to each of these samples based on their locations. So in order to do this, we can use a block weighter. So in GeoStats, we have this other spatial operation called the weight, that I can weight this sample with a block weighter. I'll also set the block size to be 50 by 50. And what we'll notice here is that it will produce this vector of weights, which are also spatial. I'll save these weights into a variable W, and I'll plot them here, and I'll set the color map to oranges. So what this weight function does, it creates the partition with the block partitioner as above, and does the counting and takes the reciprocal of this block counts as the weights. As you notice, most of these weights are high for samples that are isolated, whereas samples that are clustered and redundant receive low weight. So these weights, they are a function of the block size b square that I've chosen, in this case 50 by 50. And they can be used as a weighted average of this form, where I weight every sample in my spatial sample with a weight. And this weighted average here generalizes the sample average when you make this block size tend to 0. So if I make block sizes which are so small that they only contain a single dot, I recover the sample average of this spatial sample. In order to understand how this weighted average is sensitive to this block size, we can plot this average for increasing block sizes to notice that we recover uniform weights equals to 1, when the block size is too small, or when the block size is too large. So if I pick one single block that covers the entire spatial sample, all the points will have the same weight. So in order to do this, let's first understand what's the range of block sizes we could investigate here. So in order to do this, I'll take my spatial sample S and I'll find the bounding box of the sample. That's a rectangle region that covers all the samples, and I can take the sides of this bounding box to see what's the size or the extent of this spatial domain. So I have 276 units in the X dimension and 256 in the Y dimension. I'll set block sizes that go, let's say, to half of this extent. In this case, let's say 250. Let's take 120 as my upper bound. So say I have block sizes that go from a range of 1 to 120, and I have 100 of them. I can then calculate this weighted average. I'll call it here MIS, which is calculating this mean of the spatial sample for the variable gold with a block size b for b in b's. So here, this mean operation with a block size as the third argument comes from GeoStats. If you run this, it will be performing the weighting and the blocking as we did above for the block size b. We can then create our plot. Let's create it with an X label equals block size and a Y label equals the mean estimate. And the first layer that I'll add to this plot is the layer with the B's and the Mu's, where I'll set this label to be weighted average. I'll also set the color of this to be green. And now I'll set other horizontal lines here so that we have an idea of where these estimates are. I'll also remove move the legend to the bottom right of the image so that it doesn't appear on the top of the graph. And I'll set a horizontal line at the sample average that we have computed above, and I'll set the color of this sample average to red and the line style to a dash line style, and the label will be sample average. So that's where our sample average lies, the 0.67, if I remember correctly, and that's how our weighted average looks like for different block sizes. I can also add an horizontal line for the true average of the mine, which we computed in the beginning of this as well. I'll give it a black color, also dash line, and I'll call it the true average. So as we notice, the true average is a sharp 0.5. The sample average, this red dashed line here, is much higher due to the sampling bias. However, if you do the weighted average, you'll see this U-shape profile that tries to get closer and closer to the unbiased estimate, or the unbiased value of the true average. We will see, as the text mentioned, that for very small block sizes we recover the sample average, and also if you make a block size so large we will end up assigning equal weights for all the samples and also recovering the sample average. However, we don't know how to choose this block size or an ideal block size here. In the case that we omit this block size, GeoStats will use a heuristic to select a reasonable block size for the spatial configuration. So, for example, we can compute as before, the spatial sample, the spatial average as mean of S. That's the non-spatial one. And we can also do the spatial version, which is mean of the spatial, and the only difference here is that I pass the spatial variable as the second argument. So this one here is provided by GeoStats, where I'm passing a spatial object directly, and instead of getting the array from the spatial object, I'm just specifying the variable as a second argument. You will see that if I print, for example, the sample average, I will save it here, and then I will print the weighted average with the default block size chosen by GeoStats, which is going to be the block size. And I'll also plot the true average. Which we computed in the top of the script. I'll align this so that it's easier to read. And here you see that the weighted average gets closer to the true average. We can compare this difference in the mean and the difference in volume of code that was estimated had we chosen the sample average versus the weighted average. So what's the amount of gold in that region, right? So I can, for example, take my spatial sample, get the bounding box as we did before, but now instead of taking the size, I'll take the volume of this bounding box. I'll save this volume in a variable, and I can then compute the amount of gold that I would have estimated if I had chosen the sample average. So that would be the sample average times the volume minus the weighted average, let me set it here, times this volume. So that would be the amount of gold that I would be overestimating had I chosen the sample average without using the coordinates into account. I can simplify this expression and compute it like this. So you'll notice that this spatial mean here defined in GeoStats is just one specific type of statistic. The idea of assigning importance weights to samples via spatial declustering is, however, general and holds for any statistic of interest. Hence the term declustered statistics. To give another example, we can obtain better estimates of any quantile of the gold distribution by considering the coordinates of the samples. So, like I did with the mean function, I can compute the quantile of this spatial variable, AU, but here I'm taking the vector and then calling the native or built-in quantile function of Julia, which is non-spatial. So I will take the quantile for the 25 percentile, 50, and 0.75. So this is the non-spatial quantile. Compare it with the spatial quantile defined in GeoStats. So I'm passing a real spatial object as the first argument, and instead of indexing with the variable, I pass this variable as the second argument. I do the same, 0.25, 0.50, and 0.75. You will notice that these quantiles are also always a bit smaller than the non-spatial quantiles, which are overestimating the resource because the samples are suffering from sampling bias. So I have a few remarks to finish this tutorial. We learned that spatial samples can be weighted based on the coordinates to improve volumetric estimates of resources, and we saw that if we chosen the sample average as opposed to this weighted average, we'll be overestimating this resource by this amount. We learned that spatial declustering is particularly useful in the presence of sampling bias and spatial correlation. In this case, the sampling bias is about seeking values of this resource that are high. In other situations, we could also be sampling your spatial domain, seeking values of low concentration of some variable. In this case, what you would notice is that this U shape of the weighted average would be flipped. It will be upside down version of this U shape, where the true estimate, the true average would be at the top. Your sample average would be underestimating the value of the mean, and your weighted average would be having this reversed U shape. And then we learned that GeoStats changes the semantics of statistics such as mean, var, and quantile in a spatial context. And that's what we are pursuing with this project. We want to make it a truly spatial framework where operations that are called by a user like this, they perform a set of spatial operations behind the scenes and return a different value for the quantile, the mean, and the var variance of this spatial data set.